25ページから始めます。テキストはここに行けばあります。テキスト PDF に行けばあります。コンパスの場合はここをクリックすればいけます。で、Problems です。Number 1, Poisson distribution. In the Drude model, the probability of an electron suffering a collision in an infinitesimal interval dt is just dt divided by tau. Part A. Show that an electron picked at random at a given moment had no collision. Show that an electron picked at random at a given moment had no collision during the preceding t second with probability exponential minus t divided by tau. Show that it will have no collision during the next t second with the same probability. Okay, I think this is a whiteboard. Let me see this one. Doesn't work. Okay. So let's see. The electron picked at random at a given moment had no collision during the preceding t second it's hard to do this. No collision during preceding t second. Okay, let me look up the solution. I can do this way. So one solution here. According to the Drude model, probability of an electron suffering a collision in any infinitesimal interval dt is dt over tau. Here, tau is the relaxation time, and probability of an electron suffering no collision is 1 minus dt over tau. Part 1. To calculate the probability, first divide the time t into n intervals such that delta t equal t divided by n. Also, when n go to infinity, the term lt dt lt what is this? I think this should be limit. Limit delta t go to equal delta t, and the value of delta t approaches 0. The probability that no collision occurs in time interval delta t is given by the Drude model to be 1 minus delta t divided by tau. It is important to note that probability for no collision in interval dt must hold for each time interval dt, making up time t. Therefore, probability p of t for no collision during the interval 0 to t can be written as multiplication of probability 1 minus delta t over tau for each n intervals, that is, p of tau goes to something. Substituting delta t equal t over n, p of t go to like this under the limit n go to infinity. The term on the right hand side of the above equation becomes an exponential function. So p of t is exponential minus tau over exponential minus t over tau. Therefore, the probability that when an electron is picked at random, it did not suffer any collision during preceding t second is p of t equal exponential minus t divided by tau. Given had no collision during the preceding t second, this is no. I think this solution did this part. No collision during the next t second is this. Preceding so that electron I think this is okay for the next time interval t. No collision takes place with probability exponential sub t. Well, what is the preceding? Collision. This is kind of difficult. How can we go back in time? Preceding delta t. Anyway, okay, let me skip. So that the probability that the time interval between two successive collisions of an electron falls in the range between t and t plus delta t is t tau dt over tau times exponential minus t divided by tau. Two successful it's a kind of difficult, no? The probability that the electron picked at random does not collide in interval 0 to t and then does collide in the next time interval dt can be calculated by multiplying the probability of collision interval dt with probability p calculated in part A. Pt, large P, capital P of t is pt times dt divided by tau. Here dt divided by tau is the probability of an electron suffering a collision in any infinitesimal interval dt, and pt is the probability that the electron picked at random suffers no collision in interval 0 to t. Substitute pt, small pt equal exponential minus t divided by tau in equation. Large p of t equals small p of t times dt divided by tau. So large p of t is exponential minus t divided by tau times dt over tau. It is important to note that large p of t depicts the probability that the electron picked at random does not collide in interval 0 and t, and then does collide in interval dt and is given as this. I don't know. Okay, show that the probability that the time interval between two successive collisions of an electron falls in the range. Okay, so this means first collision. We just have, this is time. The first collision, assume this is t0. Then the second collision is here. And this is, this range is t0 plus t, and this one t0 plus t plus dt. So this is more like this. Assuming that the first collision took place at time t0. What is the probability that the second collision takes place in the time interval between t0 plus t and t0 plus t plus dt. So this is the question. Assuming that the first collision took place at time t0, what is the probability that the second collision takes place in the time interval between t0 plus t and t0 plus t plus dt? And answer is exponential minus t divided by tau times dt over tau. This is the answer. Number C, part C, show as a consequence of A that at any moment the mean time back to the last collision or up to the next collision averaged over all electrons is tau. Solution. the mean time back to the last collision or up to the next collision can be averaged over all electrons as average time is, how come this is, I think we should do more precisely, we should do like this. They say, okay. I think what we should do is this. Here, 0 to infinity, p t dt, then 0 to infinity, t pt dt. Then this one, denominator is actually tau. This is more like minus tau. Infinity to 0. Equal tau. So that's why then we substitute x equal minus exponential minus t divided by tau such that t log x equal minus tau t over tau. So t is minus tau log x dt then you have this, and the limits of integration operate from 1 to 0. So you have this one. This x and this x is cancelled. So I don't know, d dx x log x minus x equal log x plus 1. Or is this like x minus 1? I'm not sure. I'm sorry, I'm not sure how we need this absolute value. Log x. Log x. Okay, sorry. Log x is something like this. This is log x. This is 1. I don't know, is this the same as this one? You have this is exponential. It's exponential x. So it's more like minus infinity to 0 e to x dx. This is like ex minus infinity to 0 is 1. This seems okay. So this thing is actually same as this one. So we can obtain this one. Okay, so therefore the mean time back to the last collision or up to the next collision average over all electrons is tau. Next one. So as a consequence of B that the mean time between successive collision of an electron is tau. The mean time between collision of an electron is evaluated by the same integral as part C, thereafter generating a value equal to tau as mean time between collision. I don't know, mean time between collision. can just evaluate in the same way. Therefore, mean time between successive collisions of electrons is tau. Okay, next. Part C. Part E. Part C implies that any moment, the time t between the last and next collision averaged over all electrons is 2 tau. Explain why this is not inconsistent with the result in D. Although explanation should include a derivation of probability distribution for T. A thorough explanation should include the derivation of probability distribution for T. A failure to appreciate this subtlety led Drude to a conductivity only half of 1.6. He did not make the same mistake in the thermal conductivity, whence the factor of 2 in his calculation of the Lorentz number. See page 23. The mean time back to the last collision averaged over all electrons is tau. Therefore, the mean time between the last and next collision averaged over all electrons is 2 tau. However, from the result of part D, one can see that the average time between successive collisions is tau. This is a paradox that can be resolved by considering the timeline of the single electron showing below. This is the collisions, and here this is the time. It can be seen from the timeline above, and when the electrons collide too often and are separated by large time intervals over timeline. It can be seen from the timeline above that when the electrons collide too often and are too often large time too separated too often and are separated by large time intervals over the timeline. Picking a particular point on the timeline is likely to land on a large time interval. When the electron I'd say or. It can be seen from the timeline above that electrons collide too often or electrons are separated by large time intervals over the timeline. Picking a particular point on the timeline is likely to land on a large time interval. This will modulate the average time interval to be larger than tau. The probability distribution for t can be calculated by using the property of convolution over the probability distribution. Small p of t equals exponential minus t divided by tau over intervals 0 to t. Large P of t is 0 from 0 to large T. P of t1 dt1 divided by tau P of large T. P of large T minus small t1 dt tau. Substitute P of t1 equal minus exponential minus t1 divided by tau, and P of t large T minus t1 equal e to the power large T minus t1 divided by. Is this should it be minus t1? For the distribution above, the average over time t complicated. Let's see. I think it's important to understand this part. I'm sorry, I have to. The probability distribution for t can be convoluted. Why? part C implies that at any moment the time large t between the last and next collision averaged over all electrons is 2 tau. Explain why this is not inconsistent of result D. I think I need time to understand what's happening. This is more like this. You have time 0. This is some time 0. Then there is a t1. So this is the probability that one collision is here. Then this is the probability that another collision is here, t. Very strange. I don't know. Let me see. What? Probability distribution for t can be calculated using the property of convolution over the probability distribution over time interval t as I think this is more like just doing the part B, part A. The same probability for going back or going ahead. So it seems like this is I don't understand. Pick one. This just looks like doing part A, same as doing part A. This just looks like doing part A. Okay, let me think about it, and